Welcome to this explainer. If you've ever wondered why a massive AI model can write flawless, complex code but completely fail at basic logic, the answer actually lies in a proprietary framework known as the energetic paradigm. Today, we're going to methodically decode this concept. We'll explore exactly how AI capabilities are formed, why they develop so unevenly, and how they can ultimately be governed. Our goal is to translate these complex structural dynamics into a measurable, observable science.
Here is our roadmap for today. We'll cover artificial jagged intelligence, the optimization energy landscape, regulating optimization energy, defining structural objectives, and finally, governance and AI sovereignty.
Section 1. Artificial Jagged Intelligence and the Uneven Capability Landscape.
You've likely noticed a specific structural property in large AI models. They have a highly uneven capability profile. On one hand, we see these massive capability peaks. They're brilliant at language generation, coding, and pattern recognition. But right next to those peaks are deep, weak capability gaps. We're talking about failures in long-term planning, a lack of cross-context consistency, and really weak real-world situational understanding. Development doesn't happen evenly. It happens in these irregular jumps. We call this exact phenomenon artificial jagged intelligence, or AJI. It perfectly describes this landscape of localized capability peaks that lack full integration across different domains. And here's the crucial thing. This isn't just some random data anomaly. It is a direct reflection of how optimization energy is allocated during the training process itself. Moving to Section 2, the optimization energy landscape, following the path of least resistance. To understand why capabilities develop so unevenly, we need to look at gradient-based optimization, the actual mechanism AI uses to learn and minimize prediction errors. Think of this loss surface as a physical energy landscape. The optimization process naturally prioritizes directions that reduce errors the fastest. So strong, clear data creates low-resistance paths where energy just flows easily. Meanwhile, weak or complex signals act like high-resistance terrain, and they get completely neglected. This dynamic kicks off a powerful reinforcing cycle. A strong gradient from dense data attracts stronger parameter updates. Those updates improve the model's mathematical representations, which then reduces the loss even further. Because it's working so efficiently, the optimizer just keeps its focus right there, building up isolated capabilities while ignoring the rest. But here is the critical catch. Training resources are fundamentally finite. There's only so much compute time and so many gradient updates to go around. Allocating a massive amount of energy to one capability inherently starves another. It's a structural zero-sum game. You simply cannot build up every capability at the same time if the optimization field is tilting all your resources toward a few dominant paths. Section 3. Regulating optimization energy, measuring and adjusting the flow. So, if energy determines capability, the next logical step is figuring out how to measure that invisible flow. This mathematical formula represents the gradient energy monitor. It compares the gradient magnitude for a specific module against the total gradient magnitude across all modules. That lets us observe exactly what proportion of optimization energy every single part of the model is receiving at any given step. Capability formation is no longer a black box. It's an entirely measurable metric. And once we can measure that energy, we can dynamically regulate it. By applying a weighting factor with an exponential decay function, the system can automatically dampen the learning rate from modules that are absorbing way too much energy. This prevents extreme concentration and preserves precious resources for those underdeveloped, high-resistance regions. We're structurally preventing imbalances without actually halting the overall learning process. Section 4. Defining structural objectives, engineering balance in AI models. Now, dynamic regulation manages the rate of learning, but we also have to change what the model is explicitly trying to achieve. This is where we introduce an energy balance objective. By adding a penalty to the total loss function that tracks the variance in energy shares, the system is mathematically discouraged from extreme imbalances. The optimizer is practically forced to distribute its updates more evenly. Furthermore, standard next token prediction doesn't really reward complex, multi-step reasoning. To fix those weak capability gaps we talked about earlier, we have to embed explicit mathematical objectives right into the loss function. Alongside basic token prediction, we add specific terms for cross-context consistency and long-term planning. Suddenly, capabilities that were treated as afterthoughts get the direct optimization pressure they actually need to develop. Section 5. Governance and AI sovereignty.
directing the optimization field.
Once energy flow is mathematically measurable and adjustable, it becomes a governable structure. Historically, AI training has been all about uncontrolled emergence, just scaling up models and waiting to see what abilities pop out. But by moving to measured distribution and managed redistribution, we achieve directed development. The model's trajectory transforms into a carefully engineered outcome.
So, what does this look like in practice? Optimization governance means implementing strict controls within the training loop itself, setting maximum energy limits, minimum allocations for critical capabilities, and clear intervention thresholds. This empowers a whole new set of actors. Developers, companies, and even national governments can now establish institutional rules that dictate exactly how these systems mature. The energetic paradigm highlights a deeply important distinction. Expanding parameters and throwing raw compute power at a model will dictate the maximum upper bounds of its potential, but it's the governance of the optimization field that decides which capabilities actually emerge first. Scaling provides the engine, for sure, but governance holds the steering wheel. I want to leave you with this final provocative thought. If controlling energy allocation mathematically shapes capability outcomes, say prioritizing medical reasoning over social manipulation, or vice versa, who ultimately holds optimization sovereignty over our future AI systems? Understanding the mechanics is really just the first step. Deciding who gets to control those parameters, that is the real challenge ahead of us.